Anshul, you can start. Huh? Yes, you can demonstrate. You can go on telling what you are doing so that everyone can do it later on. Okay. Thank you.
Uh, I've just created a new folder and I'm opening the terminal here. Uh, to run SWB, command is SWB ampersand. So like initially this directory window will be popped out, and after that you can give a like subfolder name or just uh, select it. When this window opens, you need to go to project and select new and new project. After that, you can save by giving any name, like suppose demo. It's saved now. So this is our SWB interface. Here initially there are no tools. Here we can go to this, right click and add what to say, our tools. First we need to add SDE tool. Here option should be interactive, so that like we'll get the output of each node after it's run, so that we can see whether it's correct or not. So after this we need to go to add again. Now we'll select S device. After that we want to add a S device after SD, so this option should be selected here. So now thing left is like we need to give inputs to our SDE and S device tools. So for SDE tool, we need to go here, edit input and command section. Here we need to give our SCM file, which we have already have. I've just copy paste the SCM file here in our command section. So in this, we need to change the like say structure name to n at the rate node, and messing structure name also to the same n at the rate node at the rate, and save it. This is our first change. After that as I mentioned here, in this SCM file initially it was like this, and we'll be changing like this. So now we need to copy paste our command file and change from this format to this format. Same, we need to go to edit input, commands, and save it here. This is a VD sweep of MOSFET. So as I've mentioned here, we need to do this changes. this is the first change which we did in S device. And after that, what is it? Uh, we need to we need to insert our inputs to parameter file. Just go to parameter and create a empty file. And after that, this is a VD sweep file. Here we have parameters. Just copy this and paste here. And we also need to copy this three material files and paste here. You can remember that we need to paste in the subfolder. After that, we need to change syntax little bit. As I mentioned here, we need to follow this syntax: hash define par file dir. Excuse me. So yeah, after this part is done, now thing left is like creating parameters, which will be helpful for our batch processing. So suppose in SD, I'm going to this commands file. I want to change this 1e17 into a parameter. We'll take it as in body. We need to use this at the rate to define a parameter. In this, you go here and click add parameter slash values and give your parameter name. Then you can give a list of values. Suppose my value was 1e17. But if I want to give a test for 1e18, 1e19, then we can go to log scale, take minimum value as 1e17, 1e18, 1e19, 1e20, number of values, 3. 4. Yeah, it's good now. So here what we did is like for our SDE input, we created a parameter in BDY and to give different values. So to run this, select these nodes and click here, run selected nodes. Save. So it's running. Blue indicates that it's running, green is like ready. You can see. Since this is in the interactive mode, our SDE open and this device is, you can see that parts of device are being generated automatically. Contacts, mesh, multibox. So since it's zoomed in, it can be an indication that this node process is done and we can close the window. Once we close the window, then it will show here. We got yellow color. So indication that the node has successfully run. We can also see that its status has been changed from running to done. So now it's executing load node 2. So these are the files which have which we have after the node has successfully run. If you click on this, yeah, huh. See, if you click on this dot and select dot file, it's showing here like what is being done in the node. So currently it's taking file and trying to execute the node. So I guess there is some error. This is the file which I've already done batch processing. So I guess the error was that we need to like define this materials before this. So now it should run. We'll try it. We'll clean up this node output. So while it is running, I'll go here and I'll explain you how exactly we can take the advantage of parameterization. This is a file where we took T body, TSI, uh, like body thickness, and silicon thickness and oxide thickness and channel length as variables. For better understanding, in come here. So this is a MOSFET file which we are trying to run now. So here our parameters are T body, T silicon, and channel length, and the other parameter was T oxide. So since I took 0 here, so we need to like parameterize every coordinate in our coding. So I'll show for one coordinate. For example, uh, suppose I want to do change this 200 width. That is from this point to this point in terms of T body and TSI. I need to do T body plus TSI. So we need to follow the syntax at the rate this less than and variable 1, operation is plus, and variable 2. This is syntax which we need to follow. I'll show you. In this is the same snippet of the snippet from. So here we used t at the rate less than at the rate t body at the rate, then plus, then tsi, then greater than at the rate. Same way, we need to parameterize every node. Even we need to parameterize contacts and also meshes, because we'll go to here. See, this is the node which we ran now. So here we can see that our numerical methods are being applied and we are calculating the current output. It will take some 3 to 4 minutes. So in the meanwhile, if we want to like run all the nodes at at a time, single time, what we need to do is like we need to develop this and change this interactive to batch, so that every time that SDE will not open, so that we don't need to close it every single time. We choose interactive now because to check whether our MOSFET is being correctly generated or not. So in the meanwhile, I'll show you how to do that parameterization for just one particular node. At the rate less than, so I changed this node. Of course, this code need to be this code will fail because all our other parameters should also be parameterized. If we do that like I did here, every single node I have parameterized here. So in the same way, if you do that, then it will run properly. See, it's showing that it's done now. So after adding the like inserting parameters here, we need to go to our code. So our first parameter is t body, so which is 0.150. If I want to give multiple values, see, same thing has been. Now I need to add a TSI also. We'll take two values, 0.050. So let's check the output of this node. We need to select the node first and go to this I thing and select this option PLT. I'll also show you the TDR file also. Meanwhile, we'll change this to batch. Okay. And I'll run this 4 nodes. So this is the device which we generated. Tray outer voltage. IV plot for the same. So it's still saving variables and running. So this is how we do batch processing. For suppose I'll show you how to visualize multiple nodes. Since this file is running, I'll open the file which has already run. So here this file is the one where we took channel length variation, oxide variation, silicon and body thickness variation. Suppose we want to visualize for how our current is varying for a particular set of body thickness, silicon thickness, and oxide thickness, and different values of channel length. So we need to go here in the same way as visual. It's loading. Okay. We need to select this S device files. I'm selecting all the 5 PLT files. Am I still connected? We'll check the status whether it's running properly or not. See, this node has successfully been run in before. There was a pop-up for the SDE. Now it's not like that. So this exhibition drain outer voltage. So this is how we visualize multiple plots at a single time. Similarly, if we want to check for the variation of drain concentration, suppose. So I'm taking a value. I'm s- I'm selecting a node for which we have constant body concentration and constant source concentration. See 5E18, 5E18, 5E18. And our drain concentration is varying 5E18, 19, 20. So we can select these three nodes and click again, visualize. So from here, a process is similar. So we will check how our simulation is going on. So our SD files are ready. Now this device is taking the have taken the output and running. So here it's saying N5, but it's hard to locate N5 here. So we need to go to view and select go to tree options and select show node numbers. So now we can easily see that this is N5 node. While it was running, it's blue. Now it will be changed to yellow. It changed to yellow. While this node is running, I'll show you the graphs. This is drain concentration variation. These are the results which I've got from batch processing, which I've already done. Like in this workspace, you can see all the nodes are successfully run. And this workspace is for body concentration variation. Here it is for dimension variation. So I have results of the both. So this is drain current variation. Similarly, I have this was the channel and the variation current plots. Lower channel and will give higher current. This is a body concentration variation. Similarly, I have generated all the plots. You need to maintain this node number so that it will be helpful to verify if these results are correct or not, or to check which nodes does the results correspond to. We'll check if so. Yeah, this node is running. We'll wait for this node to run.
Excuse me. Meanwhile, Kaushik,
Yes.
hello. Yeah, can you also show how to save this data in the CSV files? There is
Yes,
an
sir.
option over here. Yeah. Because finally, I am telling all the students at the end of the day, it's not just, I mean, this visualization is fine. You can really verify. For example, we have always been telling in the PMMD class that as we downscale the technology nodes, the current increases, the performance improves, and all. Okay. But suppose I want to use these data in circuit designs in on cadence, or let us say we want to find out any relations on that. Okay, because these are all IV relations, right? So suppose I want to see the variation of GM, then I have to take the derivative of this, which is of course possible in synopsys as well. But I want the data which I can use for with other tools. Okay, so that is what Kaushik will tell you how to like export the data in CSV files. Yes.
So this is visual. Uh, you can go to export XY data, select all the curves, click on export.
So
So
uh,
here we can
this
see
is
that
yes. So this
like
is exactly what we actually require. Okay. So once you have got this, then you can, for example, in our research work, what we will do is this data is so synopsis visualization is necessary to know whether our device is working correctly or not. So synopsis will only give you until that much. So this data which he has produced in the CSV file, this will further be used in Python for machine learning, or else we can directly use this data as a lookup table based modeling for designing circuits using Cadence or Mentor Graphics tools or whatever tools you want. Okay, that's it. Perfect.
so
So just show this. Yes.
this has node has successfully run. So I'll just so since that we have only run 4 nodes, you might think it won't work for all the nodes. So I'll keep it run remaining. Since we ran all the nodes at the same time, it's taking so much time. So, but it's worth waiting.
Well, actually, I must tell you, like, I mean, I have got experience with this kind of a batch processing using another tool, not Synopsys or SWB. So, literally, that tool used to work for 24 into 7 for 7 or 8 days. Okay. So, the batch processing used to go away, go all around. In fact, during those 10 days, I remember I went home for Dasera and I came back, and yet my simulations were still working. So, in the long run, if you see, after 10 days, the amount of data and all which you have obtained will essentially be saving a lot of your time, because remember, in this synopsis kind of workbench or kind of a batch processing kind of thing, what happens is the tool will not be wasting any time at all. So you have essentially given all the bunch of simulations all this at the same time. Okay, so this is essentially going to be way good for the performance as well as the total time taken, rather than running them individually. Okay. Yes, Anshul, please tell something.
So we can see that there are many nodes running. So it will, I guess it will take 3 to 4 hours at least
Hmm.
to run.
Anshul has got something to say. Anshul, you
Okay.
can switch on the mic. And Anshul, do you have something to say?
Sir.
No, you raise your hand, so that's why I'm
Oh,
asking.
sorry. Sorry, sir, if by mistake.
Okay, no problem.
So I'll just recap the steps which we need to change. First thing is like in the SCM file, we need to change the saving structure to n at the rate, node at the rate. Then in the CMD file, we need to change this file format from this to this format. And after that, we need to copy the parameter material files into the subfolder, and we need to change the syntax of the parameter like materials. This all we need to include. And if we want to include a parameter, we need to follow this syntax at the rate parameter name and then at the rate. So in our example, we changed body concentration to NBDY. This is a parameter which we used. Initially, it was 1E17 and we changed it to NBDY. So here to understand this, we'll go to this diagram first. So here, initially we took it as 200 nanometer directly, but now we are changing it to T body plus TSI. We need to use the syntax variable one, operation variable two, with an at the rate and less than greater than symbol. That's it. Uh, Here we got red because I guess the node is not terminated. So I guess it will take few hours. Okay, the reason which we why we got here is like if, we didn't change the all the nodes. So if we go here, so I've changed only the first line. Remaining all the lines also should be changed. Since it's not changed, one material is overlapping other, and we are getting the wrong result. So in this case, I got to know that I need to change all the nodes. I'll go to abort and do abort. So it will stop. See, every node is changed to queued to none. If we want to export this project, we need to go to export and give our name here. Suppose it's demo now. In this, it's taking so much time. Yeah, your file will be generated and you can share it with others. So that's it from my side. Anyone having any doubts?
Thank you so much, Kaushik. Um, okay, Kaushik will be with us for this semester only. He's the fourth year student. So in the next semester, he'll be going for PS2, I guess, right?
Yes, sir.
Yeah, but he will still be in contact with us. But I strongly recommend that if you want to pursue this SWB for the future, you should uh, follow his detailed demonstration, whatever he has shown today, which will be uploaded on YouTube as usual. And in case you have any doubts regarding this, then you should meet Kaushik. And anyways, our Anshul will anyways be with us for the next couple of years. Okay. Thank you so much, Kaushik, for the excellent demonstration. In fact, thanks specifically to Kaushik for this because I have I have learned SWB from him, to be honest, because I did not know this before. Thank you, Kaushik and Anshul, because they have done an untiring effort on this for the last, I think, couple of weeks now, and they figured it out all by themselves.
My pleasure.
So, yeah, thank you so much. So, all the best. I'll then close this recording now.
Yes.